All right, in this video we're going to be looking at the yellow section of your review. So starting with number 1 here. So the first thing to remember is the cube root of x, the parent function, looks something like this. A little pinwheel type shape, little twisted line going through the origin there. So we want to figure out what is that graph going to look like when we move it up 3 units, because that plus 3 is happening after we take the cube root of x. So that means it's going to affect the graph vertically. So that means instead of being at that little turning point there at 0, 0, it's going to be moved up 3 points, which is right there. Or another way to look at it is when you put 0 in there for x, the cube root of 0 is 0, and 0 plus 3 is 3. So when you put 0 in for x, you get 3 as your answer. Now every point is going to move up 3 units. So as another significant point is when x is 1, because the cube root of 1 would be 1, but 1 plus 3 now would be 4. And same thing with the cube root of negative 1. Negative 1, when you take the cube root of that, would be negative 1. Negative 1 plus 3 would be 2. All right, now I want to work with the number where I could take the cube root of it nicely, and that's going to be the number 8, because the cube root of 8 would be 2, and 2 plus 3 is 5. So when x is 8, y would be 5. So that means when x is negative 8, we would have negative 2 as your answer, plus 3 would be 1. So when x is negative 8, y would be 1. So our graph for this would now be that little twisted line there. Okay, so the domain of this would be all real numbers, or you could have said from negative infinity to infinity. Like I said, if you said all reals, that would be fine. But just know on the test, you're going to want to make sure that you recognize when to use negative infinity to represent all real numbers. Okay, so lastly, the range then for this is that it goes from negative infinity to infinity as well. And then letter C, is a function increasing or decreasing? So remember, we read a graph like we read a book. We read it from left to right. And as I look at this graph from left to right, it is increasing from left to right. And so we would say that it's an increasing function. All right, let's look at number 2. It says, write an equation for the translation of y equals square root of x that is 4 units to the left and 8 units up. So we want to come up with the equation. And so if it's going to go 4 units to the left, remember it's the opposite of what we would think. And so our brain thinks that x minus 4 would go to the left, but it's actually plus 4 would go to the left, minus 4 would go to the right. So it's going to be 4 units to the left, so it'll be plus 4. Then outside the radical, it's going to be going 8 units up. So outside the radical, it'll just be plus 8. So that would be your answer for number 2. All right. Let's look at the back side. Let's look at number 3. So we're going to solve these equations. We want to make sure that we check for extraneous solutions. So some of these might have an extraneous solution in them. We need to check for that in each one of these. All right, so for the first one, I'm going to solve for the cube root of x by subtracting 2 from both sides. Now I have the cube root of x equals 3. And then I would undo the root by cubing each side. So I would get x equals 27. Now I want to check to see if that works. So I'm going to take and put 27 in for x. So I'd have the cube root of 27 plus 2. I want to see, does that equal 5? The cube root of 27 is 3, and 3 plus 2, sure enough, is 5. So that checks out. So x equals 27. So 27 is one of your solutions. All right, let's look at number 4. So for number 4, we already have the root by itself. So I'm going to square both sides to undo that root. So I would have 3x equaling 25. So if I divide both sides by 3, I'm going to leave this as 25 thirds. Okay, don't do it as a decimal. It's just going to be better if we kept it as a fraction to be more exact. All right, so now let's check that. So if I put 25 over 3 in for x, I would have the square root of 3 times 25 over 3. I want to see, does that equal 5? Well, these 3's would cancel out, leaving us with the square root of 25. Let me just write that. So the square root of 25, which sure enough is 5. So that checks out. So that means that 25 thirds is a solution for x. All right, let's look at number 5. So for number 5, I'm going to square both sides again to undo the root. So now I would have x squared equals 3x plus 10. Oh, I have more than one variable, so I can't do the same thing that I did on the previous two. So what I'm going to do here is I'm going to get everything equal to 0. I'm going to get everything on one side of the equation. Now I want to work with a positive x squared, so I'm going to subtract 3x, and I'm going to subtract 10 from both sides. So now I get it equal to 0. Now at this point, you could technically use a quadratic formula, but that always just takes more time, so I always like to use factoring when possible, when we're working with quadratics. And so I can use this little shortcut because our coefficient here is a 1. So I'm looking for two numbers that multiply to be -10, that add together to be -3. Well, -5 times 2 is -10, and -5 plus 2 would be -3. So I'm going to put x minus 5 and x plus 2 in. So now I'm going to just set these equal to 0. And when I do that, I get x equals 5 and -2. But let's check both of these. So for the first one, again, when we check these, we're checking them with the original equation. So before we did anything to it. So if I go back to the original, I would have 5 equals the square root of 3 times 5 plus 10. So we want to see if that's true. And then we're going to see if -2 equals the square root of 3 times -2 plus 10. So we're going to check both of these to see if they work. So for the first one, if I simplify under the radical, 3 times 5 is 15, plus 10 is 25. So I get the square root of 25, which sure enough, that's 5. So that one checks, so I know 5 is a solution. Let's try -2. So let's do the under the radical. 3 times -2 is -6. -6 plus 10 is 4. And now we can see that the square root of 4 is 2, but that does not equal -2. So -2 is an extraneous solution. So that means the only solution for this one would just be 5. All right, number 6. You're building a grandfather clock with a pendulum that swings back and forth in 1.5 seconds. And then they give us that formula. It gives us swing time in seconds based on the length of the pendulum in feet. How long must a pendulum be to swing back and forth in exactly 1.5 seconds? Round to the nearest tenth of a foot. All right, so they give me a bunch of information here, but the one thing that I want to take away from this is they give me this formula. And they tell me that, so what we have two variables, the time and the length. And the length is in feet, time is in seconds. And they say that it goes back and forth in 1.5 seconds. So that tells me that that 1.5 is my value for t. So we're not just plugging this in and solving it. We're going to have to do some math here because I got to figure out what is this L. So we're just going to put 1.5 in for t. So I would have 1.5 equals 2 pi times the square root of L divided by 32. Okay, it's really tempting to want to get rid of the square root, but we can't do that yet. We want to get the root by itself. So I'm going to divide both sides by 2 pi. So when I do that, you would end up getting 0.2387. So again, I divided both sides by 2 pi, and I get 0.2387. So now I want to undo that square root, so I'm going to square both sides. When I square 0.2387, we get approximately 0.057 equals, now we'd have L divided by 32. So now to solve for L, we would multiply both sides by 32. And when you do that, you get approximately 1.8. So 1.8 feet would be the length of the pendulum for it to swing in exactly or approximately 1.5 seconds. All right, so that's the end of the yellow section. So again, hopefully that answers your questions. If you don't, or if you still have some questions here, if this didn't answer your question, please make sure that you reach out to your math teacher so we can help you out.